Dear students, welcome to our third part of the lesson on model-driven software engineering. For all new systems, the requirements engineering process should start with the feasibility study. The input to the feasibility study is a set of preliminary business requirements, an outline description of the system, and how the system is intended to support business processes. The results of the feasibility study should be a report that recommends whether or not it is worth carrying on with the requirements engineering and system development process. A feasibility study is a short, focused study that aims to answer a number of questions. First, does the system contribute to the overall objectives of the organization? Second, can the system be implemented using current technology and within given cost and schedule constraints? Third, can the system be integrated with other systems which are already in place? The issue of whether or not the system contributes to business objectives is critical. If a system does not support these objectives, it has no real value to the business. While this may seem obvious, many organizations develop systems which do not contribute to their objectives because they don't have a clear statement of these objectives, because they fail to define the business requirements for the system, or because other political or organization factors influence the system procurement. Carrying out a feasibility study involves information assessment, information collection, and report writing. The information assessment phase identifies the information that is required to answer the three questions set out above. Once the information has been identified, you should talk to information sources to discover the answers to these questions. The next stage of the requirements engineering process is requirements elicitation and analysis. In this activity, software engineers work with customers and system end users to find out about the application domain, what services the system should provide, the required performance of the system, hardware constraints, and so on. Requirements elicitation and analysis may involve a variety of people in an organization. The term stakeholder is used to refer to any person or group who will be affected by the system, directly or indirectly. Stakeholders include end users who interact with the system and everyone else in an organization that may be affected by its installation. Other system stakeholders may be engineers who are developing or maintaining related systems, business managers, domain experts, and trade union representatives. Stakeholders range from system end users through managers and external stakeholders, such as regulators who certify the acceptability of the system. For example, system stakeholders for a bank ATM include the following: current bank customers who receive services from the system, representatives from the other banks who have reciprocal agreements that allow each other's bank's ATM to be used, managers of bank branches who obtain management information from the system, counter staff at bank branches who are involved in the day-to-day running of the system, database administrators who are responsible for integrating the system with the bank's customer database, bank security managers who must ensure that the system will not pose a security hazard, the bank's marketing department who are likely to be interested in using the system as a means of marketing the bank, hardware and software maintenance engineers who are responsible for maintaining and upgrading the hardware and software, national bank regulators who are responsible for ensuring that the system conforms to banking regulations. Eliciting and understanding stakeholder requirements is difficult for several reasons. Stakeholders often don't know what they want from the computer system except in the most general terms. They may find it difficult to articulate what they want the system to do or make unrealistic demands because they are unaware of the cost of their requests. Stakeholders naturally express requirements in their own terms and with implicit knowledge of their own work. Requirements engineers without experience in the customer's domain must understand these requirements. Different stakeholders have different requirements, which they may express in different ways. Requirements engineers have to consider all potential sources of requirements and discover commonalities and conflicts. Political factors may influence the requirements of the system. For example, managers may demand specific system requirements that will increase their influence in the organization. The economic and business environment in which the analysis takes place is dynamic. It inevitably changes during the analysis process. Hence, the importance of particular requirements may change. New requirements may emerge from new stakeholders who were not originally consulted. A process model of elicitation and analysis process you can see on this slide. Each organization will have its own version or instantiation of this general model depending on local factors. But generally, the process activities are: first, requirements discovery. This is the process of interacting with stakeholders in the system to collect their requirements. Domain requirements from stakeholders and documentation are also discovered during this activity. Second, requirements classification and organization. This activity takes the unstructured collection of requirements, groups related requirements, and organizes them into coherent clusters. Third, requirements prioritization and negotiation. Inevitably, where multiple stakeholders are involved, requirements will conflict. This activity is concerned with prioritizing requirements and finding and resolving requirements conflicts through negotiations. Fourth, requirements documentation. The requirements are documented and input into the next round of the spiral. Formal or informal requirements documents may well be produced. Requirements validation is concerned with showing that the requirements actually define the system that the customer wants. Requirements validation overlaps analysis in that it is concerned with finding problems with the requirements. Requirements validation is important because errors in the requirements document can lead to extensive rework costs when they are discovered during development or after the system is in service. The cost of fixing a requirements problem by making a system change is much greater than repairing design or coding errors. The reason for this is that a change to the requirements usually means that the system design and implementation must also be changed, and then the system must be tested again. During the requirements validation process, checks should be carried out on the requirements in the requirements document. These checks include the following: validity checks. A user may think that the system is needed to perform certain functions. However, further thought and analysis may identify additional or different functions that are required. Systems have diverse stakeholders with distinct needs, and any set of requirements is inevitably a compromise across the stakeholder community. Consistency checks. Requirements in the document should not conflict. That is, there should be no contradictory constraints or descriptions of the same system function. Completeness checks. The requirements document should include requirements which define all functions and constraints intended by the system user. Realism checks. Using knowledge of existing technology, the requirements should be checked to ensure that they could actually be implemented. These checks should also take account of the budget and schedule for the system development. Verifiability. To reduce the potential for dispute between customer and contractor, system requirements should always be written so that they are verifiable. This means that you should be able to write a set of tests that can demonstrate that the delivered system meets each specified requirement. User requirements should be written in natural language because they have to be understood by people who are not technical experts. However, more detailed system requirements may be expressed in a more technical way. One widely used technique is to document the system specification as a set of system models. These models are graphical representations that describe business processes, the problem to be solved, and the system that is to be developed. Because of the graphical representations used, models are often more understandable than detailed natural language descriptions of the system requirements. They are also an important bridge between the analysis and design processes. You can use models in the analysis process to develop an understanding of the existing system that is to be replaced or improved, or to specify the new system that is required. You may develop different models to represent the system from different perspectives. For example, an external perspective, where the context or environment of the system is modeled. A behavioral perspective, where the behavior of the system is modeled. A structural perspective, where the architecture of the system or the structure of the data processed by the system is modeled. Different types of system models are based on different approaches to abstraction. A data flow model, for example, concentrates on the flow of data and the functional transformations on that data. It leaves out details of the data structures. By contrast, a model of data entities and their relationships documents the system data structures rather than its functionality. Examples of the types of system models that you might create during the analysis process are a data flow model. Data flow models show how data is processed at different stages in the system. A composition model. A composition or aggregation model shows how entities in the system are composed of other entities. An architectural model. Architectural models show the principal subsystems that make up a system. A classification model. Object, class, or interface diagrams show how entities have common characteristics. A stimulus response model or state transition diagram shows how the system reacts to internal and external events. At an early stage in the requirement solicitation and analysis process, you should decide on the boundaries of the system. This involves working with system stakeholders to distinguish what is the system and what is the system's environment. You should make these decisions early in the process to limit the system costs and the time needed for analysis. In some cases, the boundary between a system and its environment is relatively clear. For example, where an automated system is replacing an existing manual or computerized system, the environment of the new system is usually the same as the existing system's environment. In other cases, there is more flexibility, and you decide what constitutes the boundary between the system and its environment during the requirements engineering process. Architectural models describe the environment of a system. However, they do not show the relationships between the other systems in the environment and the system that is being specified. Therefore, simple architectural models are normally supplemented by other models, such as process models, that show the process activities supported by the system. Data flow models may also be used to show the data that is transferred between the system and other systems in its environment. This picture illustrates a process model for the process of procuring equipment in an organization. This involves specifying the equipment required, finding and choosing suppliers, ordering the equipment, taking delivery of the equipment, and testing it after delivery. When specifying computer support for this process, you have to decide which of these activities will actually be supported. The other activities are outside the boundary of the system. The dotted line encloses the activities that are within the system boundary. Behavioral models are used to describe the overall behavior of the system. Normally, there are two types of behavioral models. Data flow models, which model the data processing in the system, and state machine models, which model how the system reacts to events. These models may be used separately or together, depending on the type of the system that is being developed. Data flow models are an intuitive way of showing how data is processed by a system. At the analysis level, they should be used to model the way in which data is processed in the existing system. The notation used in these models represents functional processing, data stores, and data movements between functions. Data flow models are used to show how data flows through a sequence of processing steps. The data is transformed at each step before moving on to the next stage. These processing steps or transformations represent software processes or functions when data flow diagrams are used to document a software design. However, in an analysis model, people or computers may carry out the processing. One other note about this type of diagram is that it is not object-oriented. Here you can see a data flow model which shows the steps involved in processing an order for goods, such as computer equipment, in some organization. This particular model describes the data processing in the place equipment order. The model shows how the order for the goods moves from process to process. It also shows the data stores, like orders file and budget file, that are involved in this process. Data flow models are valuable because tracking and documenting how the data associated with a particular process moves through the system helps analysts understand what is going on. Data flow diagrams have the advantage that, unlike some other modeling notations, they are simple and intuitive. It is usually possible to explain them to potential system users, who can then participate in validating the analysis. An object-oriented approach to the whole software development process is now commonly used, particularly for interactive systems development. This means expressing the system's requirements using an object model, designing using objects, and developing the system in an object-oriented programming language such as Java or C++. Generally, the models developed using analysis focus on object classes and their relationships. In object-oriented requirements analysis, you should model real-world entities using object classes. You should not include details of the individual objects in the system. As you know, objects in programming mean instantiations of some class. You may create different types of object models showing how object classes are related to each other, how objects are aggregated to form other objects, how objects interact with other objects, and so on. For some classes of system, object models are natural ways of reflecting the real-world entities that are manipulated by the system. More abstract higher-level entities such as the concept of a library, a medical record system, or a word processor are harder to model as object classes. The analysis process for identifying objects and object classes is recognized as one of the most difficult areas of object-oriented development, which requires an extensive knowledge of the application domain. Object identification is basically the same for analysis and design. Reusability of object classes is well supported in the object-oriented development. The Unified Modeling Language, UML, used in the Unified method has become a standard for object modeling. The UML includes notations for different types of system models. An object class in UML is represented as a vertically oriented rectangle with 3 sections. The name of the object class is in the top section. The class attributes are in the middle section. The operations associated with the object class are in the lower section of the rectangle. The picture on this slide illustrates part of a simplified class hierarchy for a model of a library. This hierarchy gives information about the items held in the library. The library holds various items such as books, music, recordings of films, magazines, and newspapers. Here, the most general item is at the top of the tree and has a set of attributes and services that are common to all library items. These are inherited by the classes published item and recorded item, which add their own attributes that are then inherited by lower level items. This picture is an example of another inheritance hierarchy that might be part of the library model. In this case, the users of a library are shown. There are 2 classes of users, those who are allowed to borrow books and those who may only read books in the library without taking them away. Multiple inheritance models may also be constructed where a class has several parents. Its inherited attributes and services are a conjunction of those inherited from each superclass. The main problem with multiple inheritance is designing an inheritance graph, where objects do not inherit unnecessary attributes. Other problems include the difficulty of reorganizing the inheritance graph when changes are required, and resolving name clashes where attributes of 2 or more superclasses have the same name but different meanings. At the system modeling level, such clashes are relatively easy to resolve by manually altering the object model. They cause more problems in object-oriented programming. This picture shows an example of a multiple inheritance model that may also be part of the library model. As well as acquiring attributes and services through an inheritance relationship with other objects, Some objects are groupings of other objects. That is, an object is an aggregate of a set of other objects. The classes representing these objects may be modeled using an object aggregation model, as shown on this picture. In this example, a library item is modeled, which is a study pack for university course. This study pack includes lecture notes, exercises, sample solutions, copies of transparencies used in lectures, and videotapes. The UML notation for aggregation is to represent the composition by including a diamond shape on the source of the link. Therefore, this picture can be read as a study pack is composed of one or more assignments, overhead projector slide packages, lecture notes, and videotapes. To model a system, the most important aspect is to capture the dynamic behavior. Dynamic behavior means the behavior of the system when it is running or operating. Only static behavior is not sufficient to model a system. Rather, dynamic behavior is more important than static behavior. In UML, there are 5 diagrams available to model the dynamic nature, and use case diagram is one of them. Now, as we have to discuss that the use case diagram is dynamic in nature, there should be some internal or external factors for making the interaction. These internal and external agents are known as actors. Use case diagrams consist of actors, use cases, and their relationships. The diagram is used to model the system or subsystem of an application. A single use case diagram captures a particular functionality of the system. Hence, to model the entire system, a number of use case diagrams are used. Use case diagrams become a fundamental feature of the UML notation for describing object-oriented system models. In their simplest form, a use case identifies the type of interaction and the actors involved. There are actors and interactions in use case diagrams. Each class of interaction is represented as a name named ellipse. The set of use cases represents all of the possible interactions to be represented in the system requirements. An actor communicates with the use case via the communicate relationship and expects from it some feedback, a value, or observable result. UML stereotypes allow designers extend the vocabulary of UML in order to introduce new concepts into a model. There are usually 2 typical viewpoints. No actors is used when only use cases and their relationships are present in the diagram. And single actors viewpoint is used when all use cases are for each important actor. A use case diagram is composed of actors, use cases, and various interrelationships among actors and use cases. These interrelationships can exist among actors, among use cases, or between actors and use cases. Actors and use cases are related using the default communicates relationship. Actors can be related using the generalization relationship. Finally, use cases can be linked together using the extend, include, and generalization relationships. Please take a close look at this use case diagram. An actor represents someone or something that interacts with the system and expects some useful results. An actor is represented by a stickman with the unique actor name next to it, as shown on this picture. Actors are viewed as entities that are external to the system. Actors include people or other external systems. Different results are expected when interacting with different use cases of the system. A use case must primarily satisfy some functional requirements. The functional requirements are listed as the steps followed in the use case. A use case is represented by an oval with the use case name inside of it. An actor interacting with the use case is linked with that use case. A line represents the fact that the actor and use case communicate. An optional directed line with an arrow pointing at the use case indicates that the actor initiates or triggers the communications with the use case. A plain line indicates a two-way communication between the actor and the use case. An actor initiates or triggers the communication with the use case to request a service through that use case. However, a use case communicates with an actor to prompt the actor for input on a decision, or to inform the actor of events or decisions made by the system. An actor can communicate with several use cases. Also, An actor can play various roles with different use cases. Furthermore, many actors can communicate with the single use case. However, one of the actors is often the initiator of the communication with the use case. Relationship include means that the execution of one use case always contains within the functionality of the included use case. For example, withdraw money base use case includes check account balance additional use case. Includes allows the common functionality to become common and accessible for other base use cases, and it also reduces the complexity by extracting additional use cases. Relationship extends means the execution of one use case may need to be extended sometimes by the functionality of the extending use case. For example, print transaction record extension use case extends withdraw money base use case. Extends is used for modeling exceptional or optional behavior. Importantly, the base use case does not depend on the extension for its own functionality. Let us read this use case diagram for movie actor. The cinema employee can create, update, and delete movies from the movie database. In addition, an employee can create, update, and delete movie screenings from the screening database. The moviegoer can request the display of movie actor details and then optionally select a particular movie to display its screening details. A manager can request the display of summary reports on movie actor information and screening details. When creating or updating the movie screening information, some basic check for conflict and availability of a screening room is completed before committing to the change. A structured method is a systematic way of producing models of an existing system or of a system that is to be built. They were first developed in the 1970s to support software analysis and design. Structured methods provide a framework for detailed system modeling as part of requirements elicitation and analysis. Most structured methods have their own preferred set of system models. They usually define a process that may be used to derive these models and a set of rules and guidelines that apply to the models. Standard documentation is produced for the system. Computer-aided software engineering tools are usually available for method support. These tools support model editing and code and report generation and provide some model checking capabilities. Structured methods have been applied successfully in many large projects. They can deliver significant cost reductions because they use standard notations and ensure that standard design documentation is produced. However, structured methods suffer from a number of weaknesses. First, they do not provide effective support for understanding or modeling non-functional system requirements. Second, they are indiscriminate in that they do not usually include guidelines to help users decide whether a method is appropriate for a particular problem, nor do they normally include advice on how they may be adapted for use in a particular environment. Third, they often produce too much documentation. The essence of the system requirements may be hidden by the mass of details that is included. Fourth, the models that are produced are very detailed, and users often find them difficult to understand. These users therefore cannot check the realism of these models. To recap, this was our third lesson on software engineering, in which we have covered such topics as feasibility study, stakeholders, elicitation and analysis of requirements, validation, system modeling, model types, object models, object aggregation, and use case diagrams. I'll see you in the next class. Thank you very much.